So, we have already introduced an important chunk of the math in special relativity. Time dilation, length contraction, Lorentz equations. We have also introduced the space-time diagram, also known as Minkowski diagrams, after Hermann Minkowski, who introduced them in 1908. In them, we represent the position x as our horizontal axis and the time ct as our vertical axis. We also know that we can represent the axis of two inertial frames in the same Minkowski diagram. We have the axis of the moving frame tilted with respect to the rest frame. The tangent of the angle between x and x prime axis is the relative velocity beta. The same for the ct and ct prime axis. I'm going to show you now how we can see all of the length contraction, time dilation, and loss of synchronization effects in these two observers' diagrams. To quantify the space-time diagrams, we need to calibrate each of the axes, x and ct. It is clear how to do that for the rest frame. Remember that we are using x and ct so that we measure space and time with the same units, and a line making 45 degrees with each axis is going to be the world line of light. But what about the calibration of the moving frame? For that, I am going to use the space-time interval, that invariant that we've recently found. So here we have the rest frame in black, the ct and x axis, and then the moving reference frame with the ct prime and x prime axis. This dotted line is the world line of light, and this angle, the tangent of this angle, is beta, the relative velocity. For example, let's think about an event P taking place here. If we want to look at the coordinates, what we usually do is just trace some lines parallel to the axis. Let's look at the ct to find this dotted line is parallel to the ct, and then here we have, this will be the x component of point P. And for the time, we look at a line parallel to the x-axis, and then we have that this is going to be ct of point P. Do the same for the other reference frame. For the moving reference frame, we draw a line which is parallel to the x prime. Then we do something like this, and this will be the ct prime coordinates of P, and then a line parallel to ct prime, something like this, and this point will be the x prime coordinate of P. So we can see that, well, the coordinates are different. We have that this length here is different to this other length, this length here is different to this other length, but in one reference frame that will be ct prime of P, x prime of P, or in the other one ct of P, x of P. We can just go from one to the other by using Lorentz transformation equations. But now what we are going to do is to use the space-time invariant to find a mathematical relationship so we can calibrate all these axes here. So I'm going to use the space-time interval, this invariant here, and I'm going to use the origin as one of the events. So instead of writing delta s squared, I will write s squared equals to ct squared minus x squared. So let's, just for fun, assume that s squared is going to be plus 1. So for s squared equals to 1, then we have that 1 is equals to ct squared minus x squared. This is the same for all observers. Remember that this is an invariant, so I can also write 1 is equals to ct prime squared minus x prime squared, exactly the same. So, and for as many primes as you want for all the observers. So now what I'm going to rewrite this equation as ct squared. I will move this x squared to the other side, and I have that ct squared is equals to x squared plus 1. This equation is the same for all the observers. So now just assume that I am at the origin of my reference frame. So for me, x is going to be 0, right? So at x equals to 0, then this equation is going to be ct squared equals to 1. So this is telling me what's where the first tick in my axis, in my calibrated axis, is going to be, where time is equals to 1. So this is going to be this position here. But that's going to be for all the observers. So have a look at this equation. Let me just plot this equation. So I have an equation which is ct squared, sorry, this is square missing here, square missing there. So I have c squared t squared equals to x squared plus 1. I have two variables, horizontal or vertical. I can just plot that. And that is a hyperbola. And that hyperbola, it looks like the following thing. So it starts here and then goes asymptotically to the world length of light. So this curve here is this curve here, which happens to be the same for all the observers. If me in my reference frame, I impose that x is equals to 0, I have the tick of time equals to 1, which is this mark here. Now, but another observer in the blue reference frame will use the same equation with the same plot and say, okay, I'm going to be on my reference frame, x prime equals to 0. X prime, this is the line of the other observer, and this is going to be that x prime equals to 0. So this is going to be ct prime equals to 1. So this is going to be 1 second for me. That is going to be 1 second for the other observer. I can do this exactly the same. Instead of imposing a 1 here, a 2, and I will have a 2 here, and then I will have the same. This will be the 2. So look at this length here. This is the time interval of 1 second in the moving reference frame, and this is the time interval of 1 second in my reference frame, which is at rest. Now, that way I can calibrate the time axis. If I want to calibrate the x-axis, I will do something very similar. I will use that equation. For example, instead of equals to 1, I will impose that s squared is equals to -1. Therefore, this equation here is going to look like -1 equals to ct squared minus x squared. I'm going to solve for x here, so I move the x that way. X squared is c squared t squared plus 1, and imposing that time is equals to 0, because this axis here is this blue one or the red one. Let's look at the red one, which is my reference frame. So all these points here are the points that are at times equals to 0. So imposing that t is equals to 0, then I have that x squared is equals to 1. So I have, if I plot this hyperbola, again, it's going to be a curve like this one, asymptotic there, and this other one also, and this is going to be time position equals to 1, this is position equals to 1 also for the other reference frame, that would be 2, that would be 2, and so on. So these hyperbolas here are the ones that are going to help me to calibrate my axis. And look at this distance would be 1 second in the moving reference frame, this will be 1 meter in the reference frame, and this will in the moving reference frame, and the red one is going to be 1 meter in my rest reference frame. This is a hyperbola graph paper, where what I have here is that this will be the time axis in the rest reference frame, this is the x-axis in the rest reference frame. These are all the hyperbolas going through 1, 2, 3, 4, 5, 6. And if I draw the tilted axis of a moving reference frame, I can calibrate those axes by just using this hyperbola graph paper. Let me draw now here. This will be the axis of position, and this is going to be the axis in time. XCT. Now, assume there is a moving reference frame which, let's say, it's like a 80% of the speed of light. This is going to be the axis. So those are going to be the axes. Look at, for 80% the speed of light, then I know that I have to move 5 and then 4, and that will be 80%. This is going to be x prime. This is going to be ct prime. So look at the angle with respect to the world line of light is the same. Now this is going to be 1, 2, 3. In this case, this crossing point, this is going to be 1. This is 2. This is 3, and that's for the t-axis. For the x-axis, this is 1, 2, 3, and I have Yeah, 1 here, 2 here, 3 there. Now, imagine that that's a car moving to the right. Assuming that James Bond car moving to the right, this is the word line of the rear part of the car. Something parallel to this one is going to be the word line of the front side of the car. So this is the front side of the car, that's the rear part of the car moving to the right. So in this reference frame, we see that it makes 1, 2, 3, 4, and 5 meters, but in the moving reference frame, it's going to have a different length, which is this 1, 2, 3, 4, 5, 6, and almost 7 meters. So that is a long track. This is 7 meters long track in one reference frame, but because it's length contracted, we only see those 5 meters. That's just Lorentz contraction. What about time? Well, assume that James Bond counts to 3 in his reference frame. He says 1, 2, and 3 seconds. How long was it in the reference frame? Well, this time comes here, and it would be 1, 2, 3, 4, about 4.5 seconds, while for James Bond it was only 3 seconds. So here we also see time dilation in this space-time Minkowski diagram.